All right, today we are unlocking one of the fundamental secrets of how computers think, and it's all about simple patterns and the really powerful rules that govern them. What we're talking about are regular languages. So let's dive right in.
So, here's how we're going to break this down. First, we'll get a handle on what these languages actually are. Then, we're going to explore this really key concept called closure. It's what lets us build new stuff from simple pieces. After that, we'll see how we can ask simple questions about them and actually get clear answers. And finally, the big payoff. We'll connect it all back to the tech you use every single day.
All right, let's jump into section 1. What on earth is a regular language? Now, I know it sounds a little intimidating, but I promise you, the basic idea is something you already get.
I mean, have you ever really thought about it? How does find and replace in your text editor actually work? Or, when you type a complicated search query with all those special characters, how does the system have any clue what pattern you're looking for?
Well, the magic behind all of that? That's exactly what we're talking about today. Regular languages are kind of like the basic instruction sets, these simple little rule books that define patterns in a way a computer can understand with zero ambiguity.
Okay, so what makes these simple rulebooks so incredibly powerful? It comes down to a property called closure. You can think of this as the secret ingredient, the thing that lets us build really complex stuff out of very simple parts.
So, what exactly is closure? Well, think of it like this. Imagine you have a box of things, like, say, a box of Lego bricks. If you perform an operation, like snapping two bricks together, the result is still a Lego creation. It still belongs in that same box. The set is completely self-contained.
Let's make this crystal clear with a super simple example. Think about integers, right? The whole numbers. If you add any two of them, say 2 plus 3, you get 5, and 5 is still an integer. So we say this set of integers is closed under addition. But now, let's think about odd numbers. What happens if you add two odd numbers, like 3 plus 5? You get 8, which is an even number. You've jumped outside the set of odd numbers. That means the set is not closed under addition. See? Simple, right?
Okay, so now that we've got a handle on what closure is, let's see how this all applies to regular languages. This is where the fun starts, where we actually see how we can combine these simple building blocks to create brand new, more complex patterns.
So, the first and probably the most straightforward closure property is something called union. It's basically just like mixing two collections together. If you've got two regular languages, L and M, their union is just a new language that has every single string from both of them. And here's the crucial part. That new, bigger language is also a regular language.
And we can see this exact idea right here in the source notes. You've got one language, L, which is all the strings that start with a 0. Then you have another language, M, for strings that start with a 1. Well, their union is just a new language of all strings that start with either a 0 or a 1. We just combined them, and the result is still a perfectly valid regular language. It stays in the box.
All right, let's look at another cool property, reversal. And this one is, you guessed it, exactly what it sounds like. If you take every single string in a regular language and just write it backwards, the new set you get with all those reverse strings is also a regular language.
And again, the source material gives us a perfect, simple example. If our language L is the set with the strings 10, 001, and 110, its reversal is just 01, 100, and 011. We've completely transformed it, but it stays within that world of regular languages. It's closed under reversal.
Okay, how about this one? Complement. The complement of a language is basically everything that's not in that language. Imagine the entire universe of possible strings. The complement is that universe minus the ones you started with. And what's so amazing is that for regular languages, this set of everything else is also a perfectly structured, predictable regular language.
And this is where things get really, really cool. See, once we know a few of these basic properties, we can start using them like building blocks to prove new ones. We've just established that regular languages are closed under union and complement. Well, it turns out that's all we need to prove they're also closed under intersection.
This right here is De Morgan's law, and it's just a perfect example of how elegant this whole system is. I know, the formula might look a little complicated, but all it's really saying is that to find the strings that two languages have in common, their intersection, you can do it with the tools we already have. You just combine everything that's not in L with everything that's not in M, and then take the complement of that whole new set. We literally just built a brand new tool, intersection, using only union and complement. It's fantastic.
Okay, so let's switch gears a bit. We've been talking about building new languages, combining them, transforming them. But what about analyzing them? What kinds of questions can we ask about the languages we already have?
So we know we can build and combine and manipulate these languages in all these predictable ways. That's great. But can we actually interrogate them? Can we ask a simple question and get a straight, definitive yes or no answer? Well, that's exactly where decision properties come into play. A decision property is basically a guarantee. It's a promise that there's some kind of procedure, some algorithm, that can always give you a yes or no answer to a specific question about a language. No maybe, no I don't know.
And as you can see from the source notes, the most fundamental question of all is the membership question. It's super simple. You've got a language, L, and some random string, let's call it W. The question is just, is this string W a member of my language, L?
And for regular languages, the answer to that question is always a computable yes or no. Always. There's no maybe, there's no well, we're not sure. And honestly, that absolute certainty, that's one of their superpowers.
Okay, so we've gone through a bunch of theory here. Let's bring it all back home. Let's connect these properties to the real world. Because you might be asking, so what? Why does any of this actually matter?
Okay, let's put it all together. The closure properties? They mean we can build really complex pattern matchers out of simple little pieces. The decision properties? They mean we can reliably check if something matches our pattern. So when you boil it all down, these languages are predictable, they're buildable, and they're verifiable.
And that combination, predictable, buildable, verifiable, that is the absolute foundation for so much of the technology we use every single day. We're talking about the core logic behind search engines, the way a virus scanner identifies a threat, the way a compiler checks your code for mistakes, even something as simple as the syntax highlighting in your text editor. All of it all relies on these fundamental properties we've been talking about.
So the next time you hit Find and Replace in a document or type something into a search bar, just take a second to remember these powerful, simple rules working tirelessly behind the scenes. And it really makes you wonder, doesn't it? If these elegant, simple building blocks can power so much of our incredibly complex digital world, what other elegant, simple rules are out there, quietly shaping the complex systems all around us?